Good morning. I would like to thank you for being present in this final year project, and I would like to acknowledge my tutors from both universities, the UHI and the INSA of Lyon, as well as all the people that have made this project possible. The planning of the presentation will respect the planning of the project. First, the objective of the project and the background of it will be presented, and an introduction to rotordynamics will be made. Following this introduction, the two parts of the project will be summarized. Finally, I will conclude with questions and debate. I must remark that this project has been carried out in two research projects. The first one consists of improving the balancing procedure of centrifugal compressors in the part of balancing. These kind of compressors are called integrated compressor line, which is ECL. And the main objective is to add a value to the product in order to differentiate it from the others. And this has also two results, which is lower cost maintenance and the increase of the lifetime. The second part is a research project based on alternative control procedures based on the principles of fuzzy controllers. The idea of this part of the objective is to assess the performance of these controllers compared to PD classical controllers using two types of response: the response to imbalance and the response to an impulse during rotation. In the following slides, I will present the basic elements of a ECL compressor that you can see here. We are only going to center ourselves in the rotating parts. The rotating parts are composed by the shaft, the thrust bearing, the impellers, the pistons, the spacers, and finally the drive shaft. The drive shaft is the element that allows the transmission of power from the electrical motor to the compressor. The impellers are the points in which we accelerate the gas. And the thrust bearing is the point in which axial forces are compensated. So if we take the rotating parts, and you can see here the detail, we can create a finite element model considering beam elements that have 4 degrees of freedom, as you can see here, per node. And the main characteristic is the radius of the section. So once the finite element has been created, we are going to move on to the equations of movement, which are obtained from the Lagrange equation that is written here. Once the equations are discretized, we are able to calculate the elementary matrices of the differential system of equations that you can see that it's ordered to. The matrices are the mass, damping, and stiffness matrices, in which gyroscopic effects are also considered. The external forces are here on the right, which are caused by unbalance. And in order to aid the resolution of this system, usually we use state space representation, in which we obtain the dynamic matrix and the command matrix in function of the different matrices shown above. Once equation 3 or 2 is solved, we are able to obtain the amplitude and the phase of the displacement for each node. If the equation is solved for different speeds, we are able to plot the black line here. At the same time, we are able also to calculate the evolution of natural frequencies of the system in function of speed. And the intersection between the speed of the rotor and the natural frequency gives what are called the critical speeds. They are the points of maximum amplitude, as you can see here. Notice that we have two types of lines: the dashed line, which corresponds to the backward whirl, and the continuous line, which corresponds to the forward whirl. This is caused by the gyroscopic effects. So this is the best way of analyzing a rotor, or the dynamic behavior of a rotor. Another important result comes with this chart, in which we represent the evolution of the critical speeds in function of the stiffness of the bearings. So what we can see here is an evolution from rigid modes to flexible modes, in which the stiffness of bearing has been increased. This chart is important whenever we change from one type from bearings to other, in order to see which is the influence of bearing stiffness on critical speeds. Having introduced the principles of rotordynamics, we're going to move on to balancing. In order to understand the balancing procedure, I'm going to use an animation in which we start by the balancing of the shaft. As you can see here, the main parts of this procedure are the fixed supports, composed by rollers, in which piezoelectric sensors are going to measure the forces, and we are going to compensate these forces using two balancing planes. Here you can see VP1, VP2. The equations used to obtain the corrections are the equilibrium of forces and momentum. That gives a geometric relationship between the external forces and the corrections. We repeat this rigid balancing because we are below the first critical speed for all the elements that we're going to attach to our shaft. After the shaft is completely assembled, we are going to move to speeds above the first critical, so our compressor is going to be flexible. In these cases, we have to use another method, which is called the influence coefficient method. In this case, what we do is we analyze the vibration before and after adding a mass, and we calculate the complex value in reference to this vibration. In fact, what we do is subtract the final from the initial state from the final state, and we divide by the value of the imbalance, the added mass. So finally, what we are able to do is, for a certain number of speeds, sensors and planes, we can minimize the external imbalance and minimize also the maximum amplitude of the system. Nevertheless, when we take this compressor that is completely balanced and we put it in the final configuration on magnetic bearings, the AP criteria is not satisfied. And this is the main problem of this first part, that can be also seen in this chart here. So as I have said before, here we have the dynamic response to a run-up with the old bearings, and when we change to magnetic bearings, we have an amplification factor, usually in the third critical speed. So that shows that the correction masses are bearing dependent. Okay. The solution to this problem can be sought by adding a numerical estimation for this transition between bearings. I'm not going to explain the equations in detail, but I have summarized the information using these blocks. So the actual procedure consists of measuring the displacement, minimization, and introducing the correction for a type A of bearings. My proposal is to introduce the variations between one type of bearing to other using numerical estimations, and this is what is summarized here in this box. So we have finished the part of balancing, and now I'm going to show using a simulation why active control is also necessary in order to have a desirable response, okay, of the compressor. So this is a perfectly balanced rotor, and what we can see is that although the peak response is optimized after surpassing the critical speed, that will be here, okay, we have a transitional effect that is caused by the the transition between what is called the backward whirl and the forward whirl. You can see these important changes of amplitude, and then we attain the permanent regime. So this is an argument to introduce an active control to the system. In this slide, I've tried to summarize the control diagram, in which you can see the real model here, represented by a state space model, in which we have used modal matrices. This allows for calculation in real time, and what we're going to measure always is the displacement, but using also a modal estimation, because we use two sensors, but nevertheless the control point is not accessible. Finally, an important hypothesis is that we need to linearize the model using the inverse transfer function of the magnetic actuator. Okay, EMA stands for electromagnetic actuator. So here you can see the real, well, the compressor, the test rig, and in this block you can see how we can create a model of this real system. Now we're going to focus on the dimensionment of the controller. So we're going to use first of all a PD controller, fuzzy and fuzzy modal controllers. And the way of assess this type of controllers will be compare the response to unbalance and to impulse. I believe that fuzzy controllers are quite interesting to analyze separately, so I'm going to do a short introduction to them. Fuzzy logic, it's based on human reasoning, and as an example, let's consider a water tank in which temperature can be considered as hot or cold. So we have the universe of speech that will be hot and cold, and let's define also membership functions that you can see here in order to translate these numerical values of temperature into the different sets, and this process is called falsification. So using logic a logic controller, we're able to write the rules in a linguistic form. So what human being will do is, if the water is considered cold, he's going to add hot water, and vice versa. And finally, the diffusification process consists only on doing an inverse process at the as we have done at the beginning, and we obtain the output force, or the output command. So these are the bases concerning fuzzy logic, but we can also apply them to rotating machines. And the aim of the next slide is to show the benefits or the differences between using a classical PD or fuzzy controllers. The first thing we can see here is in all cases, all control systems reduce the maximum peak response. Here you can see displacement, and here you can see current. The other point is the transition regime that you can detect in the uncontrolled system. It's has disappeared when controlling the system. PD controllers, as you can see here, are more stiff because the critical speed has been displaced. This is similar to the critical speed map that we have shown at the beginning of the presentation. And regarding the consumption, the PD controllers represent the maximum consumption, and fuzzy modal controllers represent the minimum consumption. Nevertheless, this is a really ideal representation of the controllers. What we have to do also is introduce the influence of real noise. In this case, the noise identified experimentally is of 8 micrometers peak to peak, and we can obtain similar tendencies as we've noticed before. Nevertheless, we can also remark that the PD controller represents a high sensitivity to noise. So I believe, yes, in this slide I have summarized what I have said in words, and I will only like to emphasize the fact that 5 points have to be compared at each time, that are the maximum peak responses, the energy consumption, the dynamic force, the settling time, and the noise sensitivity. Here I have used some numerical values to compare them both. For example, in terms of energy consumption, the fuzzy model represents a 60% lower than a PD controller, and the other important results is that fuzzy controller without the model part, it's much lower than the fuzzy model or the PD. And finally, regarding the noise sensitivity, PD controllers are much more sensitive to noise than the other two. Well, let's finish this presentation by summarizing what we have seen. And I will say that the most important point is that finite element modelization has been a decisive tool for reproducing the behavior during balancing, and also it has allowed us to compare and assess numerically the different control approaches. The other important point concerning the first part of the presentation is that balancing masses are very independent, and regarding the second part of the project, the main conclusion is that fuzzy controllers are as competitive as PD controllers, are less sensitive to noise and to other gap uncertainties or experimental variations, and they are also interesting because they can reduce the dynamic force, which means that we can use a smaller actuator. Regarding the future work, it's important to say that it will be necessary to create standards for fuzzy controllers. It will be also important to try to introduce the influence of tolerances and assemblies, and the final point will be implement fuzzy controllers on industrial compressors. We are all aware that we don't have enough time to speak of all the parts of the project, but nevertheless these slides is going to show you which are the parts that we have presented here today that are marked in these boxes, and the other ones are going to summarize also the global structure of my project. So if you have any questions, you can ask them right now.